Hi, my name is Devansh Garg, and I will be presenting the research paper ZeST, also known as Zero Shot Material Transfer from a Single Image. My group is Group 54. In this presentation, I will explain ZeST, a method for transferring the material appearance of one image onto an object in another image. We will start with the foundational concepts, then discuss why material editing in 2D images is challenging, and finally delve into the ZeST pipeline, results, and implications. Foundational concepts. Diffusion models. Modern image generation often uses diffusion models. A diffusion model is a type of generative neural network that starts from random noise and gradually denoises it to produce a coherent image. Intuitively, it works like an iterative process. Beginning with pure noise, it takes many steps, where at each step it refines the image, guided by learned patterns, until a clear image emerges. Diffusion models have achieved state of the art results in generating photorealistic images, often matching or surpassing GAN based approaches. They can produce images with realistic geometry, textures, and lighting conditions. Moreover, diffusion models have been extended to conditional generation. This means you can steer the output by providing additional inputs. For example, one can condition on a text prompt, as in text to image generation, or on another image based cues for tasks like inpainting, super resolution, and style transfer. Inpainting refers to filling in missing or masked regions of an image in a plausible way. And indeed, diffusion images, diffusion models can perform this by treating masked areas as noise to be filled. Because of these capabilities, diffusion models are a powerful backbone for image editing. They can respect complex image priors while incorporating user specified constraints. ControlNet. ControlNet is a technique that adds stronger conditioning to a diffusion model by supplying structural or spatial guidance. The basic idea is to take a pre trained diffusion model, such as stable diffusion, and augment it with an additional neural network branch that processes an input condition image. For example, an edge map, segmentation mask, or depth map. This additional branch, the control net, injects features of the condition into the diffusion process so that the generated image conforms to that condition. For instance, if you feed a depth map as input to control net, the output image will tend to follow the shapes and distances implied by that depth map. ControlNet thus locks in certain aspects of the scene, like object boundaries or depth, while allowing the diffusion model to fill in other details. Researchers have shown that ControlNet can effectively enforce geometry. For example, conditioning on depth can force the scene composition and object outlines to match the given structure. In ZeST, we use ControlNet specifically to preserve the 3D geometry of the object being edited. IP adapters or image prompt adapters. An IP adapter is a module that allows a diffusion model to take an image as a prompt. In addition to text, typically diffusion models take text embeddings from a language model like CLIP as inputs. The IP adapter extends this by using a CLIP image encoder. It processes a given image through CLIP and produces a feature embedding. This embedding is then injected into the diffusion model's cross attention layers as an extra condition. In practice, this means the diffusion model will try to incorporate content or style from the prompt image. For example, if you have the photo of a person and feed it through an IP adapter with the diffusion model and also give a text prompt like in the mountains, the output will be an image of that person in a mountain setting. In ZeST, we leverage the IP adapter to extract a latent representation of the material from a material exemplar image. Concretely, the exemplar image is fed through a clip encoder. The resulting features, encoding the colors, textures, and patterns of that material, are injected into the diffusion model when editing the target image. This allows the model to learn the appearance of the material implicitly without requiring manual feature design. However, note that simply using IP adapters and text alone is not enough for our task. The ZeST authors found that naively combining an IP adapter with an image to image pipeline did not reliably transfer materials. For example, asking the model to change the apple's texture to golden bowl with a text prompt did not produce a photorealistic result, and geometry often broke down. The reason is that the IP adapter by itself entangles material appearance with object shape and context in a way that the model struggles to decouple. This motivates adding additional guidance about geometry and illumination, as we will discuss next. Depth estimation and inpainting. Basically, depth estimation from a single image, monocular depth, is the process of predicting how far away each pixel is in this scene. Today's deep learning models, such as Midas or DPT, can take an RGB image and output a grayscale depth map, where brighter pixels indicate farther distances. This provides a crude 3D understanding of the scene geometry from a single image. In ZeST, we use an off-the-shelf depth estimator, so any of the existing models, on the input image to get a depth map of the object we want to edit. This depth map then serves as a control signal. By feeding it into ControlNet, we enforce that the geometry of the object is preserved. In other words, the model knows the shape of the object via the depth, so it can keep that shape fixed while changing the material appearance. This is crucial because our method is zero shot. We have no 3D model of the object and no explicit 3D supervision. Instead, the inferred depth provides enough structural information to guide the diffusion process. The ZeST experiments show that using depth-based ControlNet indeed preserves object geometry. Without it, the model would often distort the shape when applying a new texture. Image inpainting refers to filling in a region of an image that is masked or missing. In the context of diffusion models, inpainting is done by starting the diffusion process from an image where the target region has been replaced by noise, while the rest of the image is kept intact. The model then generates pixels for the masked area in a way that is consistent with the unmasked context. This allows one to, for example, change or replace a specific object in an image while keeping the background. This can be seen as done by Google for their remove humans in an image and more. In ZeST, we use a diffusion inpainting model as the core generator. Concretely, we take the input image and mask out the object whose material we want to change. That masked image with noise in the object region is fed into the diffusion model as the initial input. At each diffusion step, we condition on the unmasked content, the original background and lighting, the depth guidance, and the material embedding. This way, the model only changes the object's appearance while keeping the surroundings and lighting consistent. And an important twist in Zest's use of inpainting is the foreground decoloring step. The authors convert the object region of the input image into grayscale before starting diffusion. Why do this? If we simply start from the original colored image, the model tends to stick too closely to the original colors, hindering the new material transfer. If we start from pure noise, the model might lose important shading cues. Starting from a grayscale version gives a balance. It removes the old color cues, but preserves the object shading and illumination patterns. The ZeST paper shows via ablation that is grayscale initialization best preserves lighting consistency in the output. In summary, the ZeST approach combines three types of input: the exemplar image, the input image's depth map, and the input image's grayscale object to drive an inpainting diffusion process. Motivation and challenges in 2D material transfer. Before diving into the meta, let us clarify the goal and why it is hard. Material transfer in 2D images means given a photo of an object, say a wooden table, and another image that shows a material, say gold or marble, create a new image where the original object now appears to be made of that new material. This is useful in graphics, e-commerce, and design. For example, showing how furniture looks in different finishes or editing art styles. Traditionally, achieving photorealistic material changes require expensive 3D knowledge and manual effort. One would need to know the 3D shape of the object, the lighting in the scene, and detailed material properties like roughness and specular parameters. It often requires specialized tools or simulations to re-render the object with new material. The ZeST authors note that 2D material editing is especially challenging because there is no direct access to this 3D information in a single photo. Unlike texturing a 3D mesh, where you have the mesh and can apply a texture, here we only have an image of an unknown object under unknown lighting. Key challenges include geometry, illumination, material entanglement. In a photo, the way an object looks is a combination of its shape, its material, and the lighting. If a statue is shiny, that could be due to either its material or a bright light. Disentangling material from these factors is hard. No ground truth data. There is no easy data set of real photos showing the same object with two different materials under the same lighting, which we could use for supervised learning. Collecting such data by photographing objects and then relighting or retexturing them is very labor intensive and expensive. Zero shot requirement. The goal is zero shot transfer. You want to take any input image and any exemplar image without retraining the model. We cannot fine tune on each new material or object. Because of these issues, the authors emphasize that their method must be training free and must rely on existing pre-trained models since no new dataset is available. The existing diffusion models and adapters have useful priors. They know about many materials and objects from the huge datasets they were trained on. ZeST cleverly taps into these pre-trained models without further training to perform the transfer. It is also worth mentioning why text-based editing is not sufficient. Some prior works have tried using text prompts to change an object's material. Example, make the wooden table metallic gold. But describing the exact look of a material with text alone is hard. Text is a poor proxy for the fine-grained visual patterns and reflectance properties of complex materials. This is why ZeST explicitly uses an image of the material as a source, which provides concrete visual information. The challenge then is how to use that exemplar image effectively. This is exactly what ZeST addresses. The ZeST pipeline, an architectural overview. The core idea of ZeST is to decompose the material transfer task into manageable pieces. One branch deals with material encoding, another with geometry, and a third with illumination. These are then fused in a diffusion-based generation process. The pipeline is illustrated in figure 2 of the paper, and I'll summarize it below. Problem setting, we have two images, a material exemplar image M that shows the desired material, example, a picture of gold or marble, and an input image I that contains an object, example, a chair, whose material we want to change. The goal is to produce a new image I dash that looks like I, but with the object's material replaced by the one in M. Importantly, all other scene elements, background, lighting, and the object's shape should remain the same as an I. An overview of the architecture gives us a good insight into the model. It uses a three-branch architecture, combining them within a diffusion inpainting process. Here is a high-level summary. Material encoding branch. We encode the exemplar image M using an image encoder, such as the clip encoder used inside an IP adapter. This yields a material embedding M that captures the appearance, colors, textures, and reflectance of the material. Geometry guidance branch. We compute a depth map D of the input image I and feed this depth map into ControlNet. This conditions the diffusion model on the object's geometry, enforcing that the final object shape matches I. Illumination guidance branch. We create a foreground mask of the object in I and use it to extract a foreground grayscale version of I, i.e., the object region turned gray, background untouched. This grayscale image I is used as the initial state for an inpainting diffusion model. The grayscale provides shading information, illumination cues without original colors. During generation, The diffusion in painting model takes these components as conditions. The material embedding M is injected via cross attention. The depth embeddings are fed through ControlNet, and the grayscale image and mask specify the inpainting region. The output is an edited image, where only the object's appearance has been changed to reflect M, while the geometry and lighting from I are preserved. We can break this down into the following detailed steps. Encode the material exemplar. So pass the material exemplar image M through the IP adapter's clip image encoder to get a feature vector M. This vector implicitly represents the material appearance. We will inject M into the diffusion model like it is a visual prompt as a condition, so the generated object looks like M in terms of texture and color. Then we prepare geometry condition. So run a monocular depth estimator on the input image I to get a depth map D. Feed D into ControlNet so that the model learns to preserve the structure indicated by D. In practice, the depth control signals ensure that the object in the generated image has the same shape and spatial layout as an eye. Prepare illumination and inpainting input. Create a mask MFG that covers the object in eye and use it to extract the foreground region of eye. Convert that object region to grayscale. Leave the background pixels unchanged and call the image eye gray. This grayscale version serves as the starting image for inpainting. The diffusion process will gradually refine it into the final edit. The mask MIG tells the model which pixels to update. Grayscaling removes color while preserving shading so the model sees how light falls on the object. Fourth and final step, run the inpainting diffusion. Now we run the diffusion inpainting. The model starts with eye gray and with some noise and iteratively denoises. At each diffusion step, the material embedding M is injected through the cross-attention layers of the UNet, the main network. This pushes the generation towards the exemplar's appearance. The depth map D is processed by ControlNet, influencing intermediate layers of the UNet. This anchors the shape to match the original geometry. The mask MFG tells the model which region is being edited. The model only changes those pixels while keeping the rest of the image fixed. The context of the unmasked background is also provided to the model, so it knows not to change the background. Through this process, the network produces a final image I dash, where the object region is now in color, no longer grayscale, and has the texture of M. But the object's shape and the scene's lighting remain as an eye. Let us see the material encoding branch in detail. We feed the exemplar image M into a clip-based image encoder. This encoder is part of the IP adapter module. Specifically, we take this feature vector output by the encoder and obtain a material embedding M. So sorry, the mic went off. This embedding is a dense vector that in some sense captures the color distribution, texture patterns, and reflectance style of M. Crucially, we do not encode M as text. Instead, we let the image itself speak through clip. Why use an IP adapter instead of text? Well, the paper compares to an alternative where one might do dream booth or another fine tuning to convert M into a keyword or embedding. These approaches compress the exemplar into a word-like token and then append it to a text prompt. However, they find that those text encoding approaches lose some information and can produce color shifts or fail to capture fine details. In contrast, the IP adapter lets us directly use the image. The authors note that simply using the IP adapter with diffusion in an image-to-image way without additional guidance did not work well. It often failed to isolate the material, mixing it with geometry cues. This observation motivates the rest of the pipeline. Geometry guidance branch. Next, the geometry guidance branch. Here the goal is to keep the object's shape fixed. We want the new material to wrap around the same geometry. If we ignore geometry, the diffusion model might warp or shrink part of the objects, since it only sees the grayscale initialization. To enforce geometry, ZeST uses the depth map as a strong prior. Concretely, we run a depth estimation network on the input image I. The resulting depth image D is given to ControlNet, which is a modified copy of the diffusion model's encoder that takes extra inputs. The depth image tells the model which parts of the object are nearer or farther, effectively encoding the 3D layout. Empirically, using this depth-based ControlNet makes a big difference. The paper shows that without it, outputs often ignore the true geometry. For example, trying to wrap the new material onto an impossible shape. With the depth guidance, the geometry information from the depth map overrides the geometry information encoded in the latent, and we can successfully transfer materials while preserving original geometry. Illumination Guidance Branch. The third branch handles illumination and background consistency. Recall that we are using a diffusion in painting model, which means we start with the input image or a noisy version of it and fill in the object region. If we simply start from a noisy canvas, the network might resynthesize background or lighting incorrectly. To preserve whatever lighting and context we have, ZeST inputs the foreground grayscale image as the initial condition. That is, we take the input image I, mask out the object region, and replace those pixels with the grayscale version of themselves. The background remains as before. This grayscale foreground ensures that the model knows the object's shape and shading, but has no color bias. The diffusion will then colorize it and texturize the object according to the material embedding, but it will do so in a way that is consistent with the object's original lighting. Technically, ZeST uses a diffusion in painting model. So the material, it takes four inputs: the material encoding M from the IP adapter, the depth map D for ControlNet, the initial image I gray for context, and the foreground mask MIG. The inpainting model is conditioned on all of these. Practically, I gray is the noisy image to denoise. At the start, an MFC indicates which pixels should be changed. The diffusion then proceeds only in those masked regions, treating the rest of the image, including the background and lighting details, as context. This way, the illumination in the input is largely preserved. If the room had warm light coming from the left, that lighting effect remains on the object as its surface changes. The ZeST paper includes an ablation, showing that using the grayscale foreground versus the original color foreground of pure noise yields the best results in terms of correct lighting. They explain using the original color biases the model too much, and pure noise loses shading clues. The grayscale strikes the right balance. After setting up these branches, the actual image generation is straightforward. Run the diffusion in painting with all these conditions. Importantly, ZeST is training free. It uses pre-trained networks, the clip IP adapter, a monocular depth estimator, the ControlNet, and the diffusion model. No part of the pipeline is fine-tuned. We'll now see the code for an implementation for ZeST. So here we can see this is the code, and here we can see we can put random images for demoing. So this is the depth map for the pumpkin. This is the input image here with the color, and this is the material exemplar. So we want to put this material onto the pumpkin. So here we can see how this would work. So the material exemplar is encoded, sent to the diffusion in painting. The input image I is sent to foreground extraction and decoloring. Here it's converted to grayscale. Then the depth map is taken and sent to diffusion and painting. The input image I is also sent for depth estimation here. We get a depth estimate, then sent to ControlNet, and that gives it diffusion and painting as well. After injection of all of this context, we get our output image I. Let's see the code now. So this code is covered under MIT license. Right. So here we can see that they import the diffuser, the IP adapter, and the depth estimator. This is how these are all the inputs to the model. And this is the final output image. We saw the architecture back there. Now let's see what's there in the code. So here we have where they load the ControlNet model. Here is them establishing the pipeline. This is the initialization for the IP adapter. Here we get our object. Here we get the target mask. This is noise injection and getting the noisy image. Here we get all the three images that we need. Here we make the image brighter to see if the image is too dim, right? So this is adjustable. Finally, after running this, we get our input images, and then we finally send this to the IP adapter. Here we get our image. So moving on to the setup and the results. So in the experimental setup for ZeST, they used a real-world dataset of 30 material exemplars paired with 30 input images. These were collected from copyright-free sources and from images generated by DALL-E 3. Each exemplar shows a clear material on an object. Each input is a different object onto which the material is transferred. This dataset tests the method's performance on diverse, challenging real images, where no ground truth is there and qualitative evaluation can be done. We've also created a synthetic dataset, 90 images created in Blender for quantitative evaluation. The authors took 9 distinct materials, varying base color, metalness, and roughness, and 10 3D meshes in the Observer's collection. They rendered each mesh once per material, giving 90 rendered images. In addition, they rendered a sphere with each material to serve as the exemplar material image. The synthetic setup gives a clear ground truth where the sphere's material is exactly the same we want on the object. Thus, metrics like PSNR and LPIPs can be computed between ZeST's output and the ground truth render. Baselines for comparison. Material transfer from a single image is a novel problem, so there are no direct prior methods. The authors construct several baselines by combining existing techniques. IP adapter plus instruct pix to pix. Here they use the IP adapter to encode the exemplar, but instead of the ZeST geometry illumination pipeline, they try using instruct pix to pix, a text-guided image editor, to apply the change, essentially changing the texture of the object prompt. This is more of an ablation to see what happens if you drop geometry guidance. Dream booth plus instruct pix to pix. First train a dream booth on the exemplar images to create a special token for the material, then use it in a text prompt with instruct pix to pix. This is similar to some mesh texturing pipelines. Dream booth plus massa control. Dream booth for material token, then use massa control, a controllable editing method to apply it. ZeST based on text. Run ZeST's full pipeline, but replace the IP adapter embedding with a text token, like change the apple to gold. This tests whether the image prompt embedding is crucial. ControlNet inpainting with text prompt. No IP adapter depth. Just do standard inpainting the text prompt for texture to show the effect of losing geometry control. Experimental results. So let's see the qualitative analysis first. Material transfer examples. ZeST produces visually compelling results across many scenarios, demonstrating that even with the most complex shapes and lighting, ZeST can successfully map one material onto another object. Some observations from those examples. Geometry preservation. In almost all cases, the object shape is clearly maintained. For instance, a statue's face remains the same, only its surface texture changes from marble to metal. The shading and highlights on the object make sense given the scene lighting. If the exemplar is shiny and the input object is curved, you see appropriate specular highlights. In the car example, a matte car becomes shiny brass, and you see new bright highlights in plausible places. Specular gloss effects. When transferring to a shiny material, the model adds specular reflections. The paper notes that for the brass car and steel dinosaur, the bright spots on the object change to match the exemplar shininess. Similarly, adding glass or plastic finishes introduces appropriate gloss. Flat plus patterned materials. Some materials are flat, like a solid color or paint, while others have patterns. ZeST correctly handles both. Example, an orange toy gets a completely flat metallic paint, whereas a patterned exemplar yields visible texture. Remarkably, ZeST can handle transparencies to some extent. For example, in one case, an exemplar showing colored glass is transferred onto another object, and you can faintly see the background through it. The model managed to apply the notion of transparency. Comparisons to baseline. So before we move on, I would like to go to the ZeST paper and show the following images. Here we can see the qualitative results on diverse materials. Here is the statue example, the orange example, the flamingo example, the car example, the Groot shape example, the frog example, the translucent material example, the jeans denim example, the figurine example, another car example. Here we can see how with the material ZeST change lighting as well. You can see the same in the dinosaur example. It's the cab example. This shows flat material versus glossy material. The mug example with sand, table example, chair example, and the Pokemon example. Let's move on to comparisons to baseline. Here we can see the comparisons of ZeST with the baseline. Methods without explicit geometry guidance. Example, plain inpainting, text prompts mangle the shape. The object may be resized, warped, or replaced by a new object that vaguely matches the prompt. They effectively ignore the original object geometry. Instruct pix to pix, with or without IP adapter, tends to preserve shape since it starts from the image, but it fails to capture the material accurately. The output may not look like the exemplar material. It often just recolors or lightly textures the object. The combination of dream booth plus massa control often misattributes the material and also distorts geometry. For example, a material meant for a mug might be spread incorrectly onto a backpack, as we can see here. Moving on. The closed baseline is Dream Booth plus ZeST geometry slash illumination branch. In this variant, they use Dream, Dream Booth to encode the material into a text token, but still use the depth control net and inpainting from ZeST. This often produces reasonable transfers, but the results have color shifts and less fidelity. For instance, the backpack example is a slightly wrong hue, as we can see, and the astronaut figure has some color bias, as we can see. This often The authors attribute this to information loss when compressing a visual material into a word embedding. Now let's see ZeST. By contrast, consistently preserves geometry and lighting when accurately applying the material across examples. ZeST performs the task effectively and retains fine details of both shape and illumination, as can be seen here. Across examples, ZeST performs the task effectively. Notably, ZeST handles the challenging transparent and occluded cases better than baselines. We can see here that the material was transferred perfectly. Similarly here, when a glass was put on the chair, we can see some hints of translucency. Moving on to qualitative results. On the synthetic dataset, 90 examples, ground truth, the authors report standard image quality metrics, PSNR, which is also called peak signal to noise ratio, where higher is better, measures per pixel similarity to ground truth. LPEPs, or learned perceptual image patch similarity, where lower is better. A learned metric capturing perceptual differences. Clip similarity, cosine similarity between clip embeddings of output and ground truth. Higher means more semantic/visual similarity. They compare the two strongest baselines from qualitative tests: IP adapter plus instruct pix to pix and Dream Booth plus ControlNet inpainting. The results are IP adapter plus instruct pix to pix 16.92 PSNR, 0.096 LPIPs, and 0.745 clip for IP adapter. Dream Booth plus GOLM guidance. Here the PSNR is 25.46, LPIPs is 0.053, and clip is 0.893. Notably, ZeST achieves the highest PSNR, lowest LPIPs, and best clip with the numbers being 25.82 for PSNR, 0.046 for LPIPs, and 0.899 for clip. Additionally, a user study was conducted on real images. 16 participants each rated random edited images and baselines on two criteria from 1 to 5: material fidelity and photorealism. The average scores were 1.48 and 3.23 for IP adapter plus instruct pix to pix, where 1.48 was the material fidelity, 3.23 was the photorealism. Dream Booth plus GOLM guidance, 3.25 for the material fidelity, and 3.41 for the photorealism. And ZeST, 4.05 for the material fidelity, and 3.78 for photorealism. ZeST significantly outperforms the other methods in both metrics. Robustness. The authors also test ZeST robustness to variations in the exemplar. Two experiments highlight this: lighting and pose change of the exemplar. You can see this here. Lighting and pose changes of exemplar. They took one material, painted on a complex shape, a pumpkin model, and rendered it 3 times under different lighting directions and rotations. They then used each of these as the exemplar to transfer onto the same target, which is a dolphin. Even if the exemplar image had different shadows or orientation, ZeST extracted the underlying material appearance reliably. This suggests ZeST is not oversensitive to the precise capture of the exemplar. The same can be seen when the exemplar material is scaled, i.e., if it is zoomed or not. We can see this here with the sofa and the weave example. So now we move on to the applications of the model. Model can be used for multiple material edits in one image. ZeST can be iterated to apply different materials to different objects in a simple image using a segmentation tool like SAM, which is Segment Anything Model. It can also be used as an exemplar-based 3D texturing. ZeST can be integrated into pipelines for texturing 3D meshes. Lighting-aware material transfer. ZeST can be used to simulate how a material would look under different lighting. The authors describe a procedure. First, apply ZeST to generate the texture of an object under one lighting, then keep the random seed fixed and rerun ZeST on the object rendered under a second lighting, using the first object as an exemplar. This way, the material's appearance stays consistent, but the reflections adjust to the new light. We also know a few limitations of ZeST, that is, but partial material transfer. Sometimes ZeST only applies the new material to part of the object instead of the whole thing. Let's see this in the research paper itself. So this is one of the applications of the model, multiple material transfers in a single image. This is exemplar prompted 3D texturing. Here is another example, the application for lighting aware material transfer. Here are the limitations. So this is the partial material transfer. Here we can see that the material was transferred only partially. Here for Goku, we see this area was not transferred. Here for the jacket, we can see that it was only transferred to the body, but up above the face is painted as it would be in a human. This is a characteristic of the underlying diffusion model, as it has learned that the human skin is the way it is. Similarly, here we can see another limitation, which is it blends multiple materials together. So the backpack material was blended with the material of the cup. And we can see it seems like the cup also has two materials, which are blended into one. Because ZeST can get confused and blend them. For instance, a tennis ball exemplar might show how both the fuzzy yellow and the white logo part might get mixed when texturing the target. This is due to the image prompt containing multiple regions. Since the IP adapter just encodes the whole image, it doesn't know to separate them. Additionally, we can also see unpredictable artifacts in the images generated by ZeST at times, as it relies on diffusion priors. Moving on to the conclusion and ZeST's impact and future. To recap, ZeST is a zero-shot, training-free method for transferring material appearance between images. It is built entirely from existing pre-trained components: a diffusion model for inpainting, a clip encoder via IP adapter, a depth estimator, and ControlNet. The magic is in how these are combined. ZeST encodes the exemplar's material in latent space, uses depth to log geometry, and uses grayscale in painting to maintain lighting. The result is a photorealistic edit that convincingly changes an object's material while leaving everything else unchanged. ZeST's main contribution is showing that complex image editing tasks like material transfer can be done by cleverly harnessing frozen generative models, and no new training data or learning is needed. The authors position this as a strong starting point. While leveraging the rich priors, diffusion models can tackle challenging graphic tasks in an intuitive way. In conclusion, ZeST demonstrates that zero-shot material transfer is feasible and opens up new possibilities for content creation. Designers can swap materials and photos with a click. 3D assets can be textured from photos, and graphics editors have a new powerful tool. The approach of combining image prompt embeddings, geometric control, and painting may inspire other zero-shot editing methods. As diffusion models and their adapters continue to improve, you can expect even more impressive and flexible editing workflows based on ideas like those in ZeST. I would like to give credit to the original authors of the paper, who are as following. Let me just present them. Here they are. I would not like to pronounce the names as I might mispronounce. These are the following universities they belong to or organizations. Thank you so much. This was Devansh Garg of Group 54 presenting ZeST, zero shot material transfer from a single image. Thank you.